Everyone knows the sun is hot, but do you know which part of the sun is the hottest? You've probably guessed it already, it's the core. Indeed, as the center of a nuclear fusion reactor, the sun's core temperature can reach 15 million degrees. In contrast, the temperature of the sun's surface, which we usually consider, is less than 6,000 degrees. This makes it seem like the sun, much like Earth, cools from the inside out. However, reality often defies intuition. Just like flames, where the outer flame is often hotter than the inner flame, the sun's temperature is far more complex than we might think. The surface of the sun that we see with the naked eye isn't its actual surface, it's the photosphere. The temperature is around 5,000 degrees. In everyday life, that's definitely high enough. You should know that over 1,000 degrees is enough to melt iron, and even tungsten, one of the metals with the highest melting points used for light bulb filaments, melts at just over 3,000 degrees. You could say that if you threw the entire Earth into the photosphere, it would melt. Although a temperature of over 5,000 degrees is already extremely high for a planet, in the family of stars it's only considered average, just a bit higher than the 3,000 degrees of red dwarfs. In the stellar family, blue giants can easily reach tens of thousands of degrees, not to mention the Wolf-Rayet stars, which are the temperature ceiling of stars. These stars can have surface temperatures soaring above 100,000 degrees. In this light, the sun's surface seems quite cool. But as you move further into the sun, the temperature rises. When you pass through the convective and radiative zones to reach the core, the temperature approaches 15 million degrees. This is the true heat engine of the sun. Here, hydrogen continuously fuses into helium, releasing enormous energy. 15 million degrees, this figure is indeed impeccable. Overall, the core is the hottest part of the sun. So where's the twist we were expecting? The twist appears in the sun's atmosphere. That's right, not inside, but outside the photosphere. Since the sun is a massive plasma ball, it doesn't have a surface in the usual sense. Outside the photosphere, there's the chromosphere and the vast corona. The chromosphere can reach temperatures of 20,000 degrees, several times higher than the photosphere. However, this is still considered normal, because when you enter the corona, you'll find that the temperature skyrockets by 2 orders of magnitude, reaching a terrifying million degrees, and in some places, even tens of millions of degrees, approaching the core's temperature. Why does the temperature rise instead of fall in the region farthest from the core? For decades, scientists have been trying to solve the mystery of the corona's high temperature, known as the coronal heating problem. At this point, some people start to comment, saying experts just love to talk nonsense, claiming whatever they can't prove, and talking about tens of thousands of degrees. Have you measured it on the sun? Believe it or not, scientists really have measured it in person. In 2018, NASA launched the Parker Solar Probe, specifically designed to explore the sun's corona. The probe is equipped with a solar shield made of reinforced carbon composite material, capable of withstanding temperatures of about 1,370 degrees Celsius. It also has advanced instruments to measure the extreme temperatures near the sun. On December 24, 2024, the Parker probe set the record for the closest approach to the sun by a man-made object at a distance of 6.1 million kilometers from the sun's surface. This distance is roughly 8.7 times the radius of the sun, and it has surpassed the boundary of the stellar wind and corona, the Alphen critical surface. It has fully entered the sun's atmosphere, the corona. During previous crossings of the corona, the Parker probe detected environmental temperatures of several million degrees multiple times, partially validating current stellar models. At this point, many people might wonder, as mentioned earlier, the solar shield can only withstand temperatures of over 1,000 degrees Celsius, but the corona is millions of degrees. Shouldn't the probe have vaporized long ago? Note that high temperature doesn't necessarily mean it's very hot. Temperature and heat are two different concepts. Temperature reflects the intensity of microscopic particle motion, while heat reflects the total energy that can be transferred between objects. In the corona, although the particles move very intensely and the temperature is very high, their density is extremely low, usually less than 1/10,000,000th of the density of air. So, although the corona's temperature is high, the heat contained per unit volume is not much. This is why the solar shield can withstand over 1,000 degrees but can resist the million-degree corona. It's just like an electric spark lighter. The voltage generated at the moment of ignition is usually thousands or even tens of thousands of volts. But because the current is extremely weak, generally only a few microamps, it only causes a slight tingling sensation and doesn't cause substantial harm to the human body. Alright, back to the topic. Has the mystery of the corona's high temperature been solved through the Parker probe's exploration? You could say it's been solved, but not completely. One thing that can be confirmed is that the heat in the outer layers of the sun mainly does not come from its interior. It has its own independent heating mechanism. The current mainstream view is that the sun's magnetic field plays a key role here. Unlike Earth's magnetic field, the Sun's magnetic field is chaotic. After all, it's a sphere composed of plasma with highly complex internal movements. Due to the rotation and convection of various parts of the Sun, the magnetic field lines on its surface often become twisted and tangled, and sometimes they break and reconnect. This process is known as magnetic reconnection. During magnetic reconnection, the vast energy stored in the magnetic field is rapidly released and converted into the kinetic energy of particles, accelerating the sparse particles in the corona to extremely high speeds, leading to temperatures far exceeding the million-degree heat of the Sun's surface. Although local temperatures of millions or even tens of millions of degrees are indeed unusual, they still cannot challenge the core's status as the hottest part. So, the real twist lies in another, even more extreme situation here. Previously, scientists calculated that during solar flares, the temperature of electrons in the corona could reach between 10 million and 40 million degrees. Later, when the Parker Solar Probe first traversed the magnetic reconnection region in the solar atmosphere, its instruments indeed detected a sudden increase in the corona's electron temperature to over 10 million degrees 1 to 5 minutes before the flare occurred. This observation serves as another strong validation of theoretical models. Thus, we can conclude that the temperature of some electrons in the corona can indeed exceed that of the Sun's core. But is that the end of it? No, even the theoretically predicted 40 million degrees is still not the Sun's temperature limit. In September 2025, researchers published an article in the Astrophysical journal Letters that presented a startling perspective. During the initial phase of a solar flare, the temperature of ions in the region above the flare loop can be several times higher than that of electrons, reaching 60 million degrees or even more. This discovery has once again reshaped our understanding of the Sun's temperature. Why does this happen? The key lies in the distribution of energy. The energy released by magnetic reconnection is not evenly distributed between electrons and ions. The ions in question are primarily hydrogen nuclei that have lost electrons due to ionization. Because atomic nuclei have greater mass, they are often able to gain stronger acceleration during magnetic reconnection. Simply put, in the same electromagnetic environment, ions receive a larger share of energy compared to electrons, resulting in a wider speed distribution and naturally higher temperatures. Additionally, due to the very low plasma density in the early stages of a flare and at the top of the loop region, collisions between particles are insufficient to quickly exchange energy, making it difficult to achieve thermal equilibrium. Consequently, the temperature of ions remains significantly higher than that of electrons for a certain period. Returning to the initial question, where is the hottest part of the Sun? From an average and long-term perspective, the core, where continuous fusion occurs, remains the undisputed hottest region. However, if we consider local and instantaneous extreme conditions, the ion temperature during flares in the corona can indeed surpass that of the core. From the millions of degrees in the corona to the tens of millions of degrees during flares, the Sun's temperature constantly challenges our understanding. The Sun is far more complex than we imagine, with each region concealing unique physical processes and mysteries. Yet, as science progresses, our understanding of the Sun deepens, which is precisely the ongoing endeavor of science. Science never offers a final, definitive answer. It only brings us closer to the ultimate truth through continuous revision and refinement.